In the last video, we talked about the Gibbs function as a discrete sum of mass times accelerations of particles. Of course, we can extend this to a continuous case of a rigid body. This integral can be expressed in terms of the acceleration of the center of mass, as well as the angular velocities and accelerations, and the moment of inertia tensor. It looks like a bit of a mess, but the derivation is straightforward. Today, we'll look at a simple two-dimensional problem and solve it using the Gibbs-Appell formulation. Consider a vertical disk rolling on the inside of a bigger fixed disk. Under the influence of gravity, we've chosen a fixed point on its perimeter. Let theta denote the angle between the vertical and the normal of the point of contact between the two disks, and phi be the angle between the vertical and the line extending from the center and the point of reference. This point of reference can be chosen arbitrarily along the perimeter of the small disk. We denote by A the radius of the small disk, and B is the radius of the big disk. We get that the condition for rolling without slipping is that the radius of the smaller disk times the sum of the angles is equal to the radius of the larger disk times theta. We can simplify this and define c to be the difference in radii, which is a distance between the centers of the disks. This is where the fun begins. We take our expression for the Gibbs function of a rigid body and we condense it down to the general case for the rigid lamina, which is like when you have a flat rigid body moving in a plane, and essentially that's how we treat our cylinder. We can omit the omega to the fourth as it vanishes when we differentiate. Before we plug in our variables, I want to mention something. Notice the dot product of the center of mass acceleration with itself. To express this in terms of our variables, we first need to look at the center of mass velocity, which we can express in polar coordinates, with c being the radial coordinate as the center of mass of the cylinder rotates about the center of the big cylinder. We then differentiate that with respect to time and collect the terms to write our expression for the center of mass acceleration. Then it's just a matter of taking the dot product. Since one of our constraints is that c must be a constant, the terms containing time derivatives of c vanish, and we can make the substitution into our equation for the Gibbs function. I've also plugged in the moment of inertia and replaced omega with the phi. Because of our pure rolling condition, we can substitute phi, and we conveniently reduce our problem to get one Gibbs-Appell equation. Since we are differentiating with respect to the second time derivative of theta, we can again omit the irrelevant terms and simplify. This is a trivial derivative. For the right side of the equation, we solve for the generalized force using last video's definition, where we use the change in work and the change in a generalized coordinate. Since we're dealing with only one generalized coordinate here, we can condense this equation. The change in energy is just the change in gravitational potential energy, and the height of the center of mass can easily be defined in terms of theta. A bit of simplification can be done to get the generalized force, and we plug it into our Gibbs-Appell equation. Simplify and rearrange the terms, and you get something quite interesting. The equation of motion is the same as a pendulum of length 3 over 2c. That's about it for now. I hope to make more videos just like this in the future. In the meantime, see you then.